As you can see in this video, we're going to be finding eventually the vertical and how to find vertical and horizontal tangents of implicit relationships. So we're going to begin. If you're in my class, you should begin by doing the warm-up on page 12. So stop the video at this time, do that warm-up, and then come back. If you're not in my class and you just want to find the lesson on vertical and horizontal tangents with implicit relationships, you'll want to move on to that part of the video. So here we go. First thing you need to do in this warm-up, you can see that we're going to be using the chain rule, is to read the directions. We're finding the derivative of f prime in terms of g prime. And the really important part is they're telling you straight up that you need to treat a, every time you see the letter A, as a constant. Now, a constant simply means that we could be treating A the same way that we would treat the number 5 or the number 7. So the derivative of 5 is 0. The derivative of 7 is 0. Therefore, when we're dealing with A, the derivative of A is 0. So let's take a look at problem number 5. We have a function whose name is f of x. And this function can be re-expressed as g of ax to the second power, written that way. And then it's a lot more easy to see that we're dealing with a chain rule problem. Our outside function here is the power of 2, and our inside function is g, and then we actually have another inside function, so it's a chain with a link of three actual functions. So when we find the derivative, we're going to begin by using the power rule. So we have 2 of that quantity. We're going to leave the inside alone to the first power. And normally we won't necessarily write to the first power, but that's just for emphasis. Then I'm going to find the derivative of the inside. The derivative of g is g prime, leaving the inside function alone again. And then the derivative of ax. Now remember, a is a constant like the number 5. So the derivative of 5x is 5, therefore the derivative of ax is a. And that's really all you need to do in this problem. They're just looking to see if you can deal with a as a constant. All right, let's take a look at problem number 6. In problem number 6, we have f of x. We have g of a, which is also a constant value. If you substitute a into the function g, you would get a number. And then we have a variable expression. I'm going to distribute the g of a to both terms inside of the binomial. So my rewrite is going to be f of x is g of a multiplied by x minus g of a multiplied by a. Now, g of a, remember we just said that g of a is a constant, and we're multiplying it by a, which is a constant. So g of a multiplied by a is also a constant. So the derivative of the second term is 0. We don't really have to write that. The derivative of the first term, we have g of a multiplied by x. So that's what we had in the scenario before, where the g of a is the coefficient of x, and the derivative of a coefficient times x is just that coefficient. So f prime of x is equal to g of a. Problem number 7. In problem number 7, we have a product. So we're going to need to apply the product rule. Here we go. The first function is x multiplied by the derivative of the second function. The derivative of the second function, let me clear that up a little bit. Sometimes this pen wants to connect things. So the first function is x, the derivative of the second. This second function requires the chain rule. The derivative of g is g prime, leave the inside alone. Okay, that's the derivative of the outside multiplied by the derivative of the inside. The derivative of a constant, g of a, multiplied by x is the constant g of a, or the coefficient in this case. All right, that was the first times the derivative of the second plus the second function, which is g of x times g, or g of x times g of a. The second multiplied by the first, the derivative of x is 1. And that's perfectly fine to determine whether or not you understand how to deal with the symbolic derivatives and the constant a. And number 8 was not assigned as part of your warm-up. All right, let's go on to the lesson. In the lesson, if you're in my class, this is on page 15 in your packet, which is where you should take your notes. In this problem, you've been asked to consider the implicit relation of 2x squared plus 2xy plus 4y squared is equal to 3. And I have provided for you a graph, as you can see here. Whoops, get rid of that. You can see here a graph which happens to be an ellipse. Our first job is to sketch any horizontal tangent lines. Now we know from, we know that the slope of a horizontal line is 0. So we're looking for places on this ellipse where the slope is 0. And that happens to occur at 2 different places. And I have actually already got my, let me see if I can grab my horizontal line here. Here's one horizontal line, and the slope is 0 here. The other horizontal line, the slope is 0 at about here. So we know already that there are 2 places, 2 values of x at which the slope is 0. I've already kind of processed that out, so I know in letter B, when I actually find the equation of the horizontal line, horizontal tangents. First of all, remember that the equation of a horizontal line is a y equal to equation. It's going to be y equal to the y value that the line goes through. We can see the we could almost come up with approximations from what you see on the 2 lines. We know that we're going to be looking for 2 different lines and looking for those equations. We also know that the slope is equal to 0, and that's where the calculus comes in, because slope would be where the derivative is equal to 0, which implies I need the derivative of this implicit relationship, which we've already learned how to do. So let's see if I can get that. I'm going to take the derivative of my function that you see up here, relationship you see up here. The derivative of 2x squared is 4x by the power rule. The second term by the product rule is the first times the derivative of the second plus the second times the derivative of the first. The derivative of the third term by the power rule is 8y dy dx. And the derivative of the constant 3 is 0. I'm going to factor the dy dx out of those 2 terms. So I have an x plus 8y. I'm going to move my non-dy dx terms, a positive 4x and a positive y, to the right-hand side by subtraction. So negative 4x minus y. Therefore, when I solve for the derivative dy dx, I get negative 4x minus y divided by x plus 8y. Notice that my slope generator, or my derivative, is x and y dependent, meaning that I have the variable x and the variable y needed in order to get the slope. Also, my derivative involves a numerator and a denominator. Now, we said that the slope of a horizontal line is 0, and we're looking for horizontal lines. If the slope of the horizontal line is 0, then the derivative is 0. But remembering that my derivative has a numerator and a denominator that I'm going to set equal to 0. If a fraction is equal to 0, we know that that 0 did not come out of the denominator. The 0 would have to come out of the numerator. Division by 0 is undefined. So really, when we have this expression, we're simply setting the numerator equal to 0 to figure out where the derivative is equal to 0. So that's my next move, and this is the algebra move. So I get negative 4x minus y equal to 0 by setting the numerator of my derivative equal to 0. Interestingly enough, that does not give me a number. It does not give me a value. In fact, what I have here is the equation of a line. Well, that's not what I was looking for. I know that my lines are horizontal, and I know that this line is certainly not horizontal. So the question is, what is that line? Now, first of all, let's take a look at it by getting y by itself. So I'm going to add 4x to the right-hand side and divide by negative 1. So I'm really looking at the line y equal to negative 4x. Well, let me slide this down, and below I have a graph of the same ellipse with the line y equal to 4x graphed on top of that ellipse. Now, very interestingly, notice that that line y equal to 4x, let me write that equation on there, y equal to 4x is a line that intersects my ellipse actually at the points I was looking for. Because if you remember, the horizontal tangent, remember we had one here and we had one here. Well, the line that we have found, y equal to negative 4x, is a line that intersects, remember upside down U means intersects the relation at the points where there is a horizontal tangent. And that's what I was looking for. Well, we're still in the algebra phase then. So what we have is a line intersecting a curve, and we need to determine where they intersect, which means where is the line equal to the curve. To do that, I'm going to use the process of substitution. If you come back up here, I'm going to take negative 4x and substitute it in place of y into the original equation. So the negative 4x is going to be substituted in place of y and in place of y. All right, so let me do that algebra. Let's see if I can keep that up there so I can see what I'm doing here. So 2x squared plus x, there's my substitution. I'm substituting negative 4x in place of y, plus 4 times, again, substituting negative 4x in place of y, equal to 3. So I end up with 2x squared minus 4x squared. I'm just multiplying here. Squaring negative 4x gives me 16x squared. Multiplied by 4 gives me 64x squared equal to 3. Combining like terms, and I will get 62x squared equal to 3. Solving for x by dividing by 62 and taking the square root is plus or minus 3 square root of 3 over 62. Now that's approximately, I went ahead and came up with the decimal approximation just so you could see, that's approximately plus or minus 0.212. Now if you come back over here to the graph, let's see if I can clean that graph up for you. Give me just a second here. Get rid of some of this stuff. I need a bigger eraser. Okay, so if you take a look at the point of intersection here and here, you can see that the x value, remember my scale right here, there's the 1. This x value right here is about 2.1, positive 2.12, and over here is about negative 2.12. However, we're not done our job yet because the problem tells me to find the equation of the horizontal tangents. Remember we talked about the equation of a horizontal line is a y equal to number. I don't have the y values, I have the x values. So to get the x values, to get the y values, I'm going to take the values of x and substitute them back into the equation of the line. So y is equal to negative 4 multiplied by plus or minus square root of 3 over, not 162, 3 over 62, which gives me y equal to plus or minus 4 root 3 over, oh, let me do a better job of that, plus or minus 4 times the square root of 3 over 162, I also found those y values, which happens to be plus or minus 0.880, which again, if you look at the graph, those are approximately where the y values lie for the horizontal tangents that we were looking at. Now, I realize there's a lot of algebra in here, which means that you're going to need to do a lot of practice to get these skills down. It's not difficult. It's just really more tedious than anything else. All right, we're going to practice that again by taking the exact same ellipse, but this time, instead of looking for horizontal tangents, we're going to be looking for any vertical tangent lines. And we're going to do the same process, the same thing. I already have my vertical lines here. So let's slide that. Oops, get rid of that. That's not what I wanted to do. Edit, undo. Wanted to grab my line. So there's one vertical tangent. And there's another vertical tangent. So let's talk about vertical lines. We know that the slope of a vertical line is undefined. And we know that the equation of a vertical line is x equal to a number. So that's what we're looking for. We know we're looking for 2. It's not always 2, but in this case, we were looking for 2 horizontal tangents and 2 vertical tangents. And to get a slope of undefined, so we have our same derivative that I'll rewrite in just a second. We have a numerator and a denominator, and the slope is undefined. Therefore, in order for the slope to be undefined, the denominator needs to be equal to 0 when we're looking for vertical tangents. Now, our slope from the other side is dy dx. This is just what we already had done when we found the derivative implicitly. Negative 4x minus y divided by x plus 8y. As I said, this time we're going to set the denominator equal to 0 because we want to know where the slope is undefined. And again, lo and behold, the same thing happens. I don't get a number out. I actually get the equation of a line. So I'm going to solve that equation, in this case, for x, because that way I don't have to deal with the fraction. I could solve for y and get 1/8 of x. But when I do my substitution, remember we're going to do a substitution into the original. This just avoids me having to deal with fractions. Now down here, again, I wanted you to see that this is y equal to 1/8 x, and that line intersects my curve at the points I'm looking for. If you compare what you see in the graph below to the one that you see above, you can see that this green line, y equal to 1/8 x, is intersecting the curve at just about the locations where above we had a vertical tangent on the left and on the right. All right, so let's do the algebra work because that's really all it is. This time we're substituting 8y in place of all of the x's. So I have 2 times 8y squared plus 8y times y plus 4y squared equal to 3. So I get 8y squared is 64y squared times 2 is 128y squared plus 8y squared plus 4y squared is equal to 3. And then when I combine like terms, you know what? I just realized, thank goodness, that I dropped a negative right here. So please take a look. This is y equal to negative 8y, not positive. So I'm going to stick a negative here and a negative here. You probably had already caught that, but now I caught it, so that's a good thing. So when I combine like terms, I get 124y squared equal to 3. Solving for y, I get y equal to plus or minus square root of 3 over 124. However, we were looking for, I'm changing colors here, we were looking for the value of x because we wanted the equation of vertical line. So these y values go back into the equation of the line. So x is equal to plus or minus 8 times the square root of 3 over 124. And if you want to take and approximate those numbers using your calculator, I think you'll see that we have found that the graphs agree with what we did in our algebraic work. The last problem that I wanted to do is page 16 in your packet. So let's just read through these instructions. We have been given the graph of a sideways parabola, and our job is to find the equation of a line. But the line is normal. Remember, we know that that tells us perpendicular to the curve at the point -2, 3, and sketch it, the line, onto the graph. So here's what I've done ahead of time. The red line is my approximated tangent line. Notice I already have the point -2, 3 identified on my graph, and this is my approximate tangent line. But that's not the line, or not the line whose equation we're looking for. We want the line that is perpendicular to the red line, and that's not quite, doesn't quite look perpendicular. Let me slant that a little bit. Actually, I'm going to slant it with my mouse. It's a little easier to operate. I just like it to look a little more perpendicular. So we are looking for the equation of the green line because remember, we were looking for, edit undo, we were looking for the equation of the normal line. So when we write the equation of a line, we know our target is y minus y1 equal to m times x minus x1, and we're looking for the equation of the green line. We already know the x and y value, so we can go ahead and start with y minus 3 is equal to, we don't yet know the slope, that's what we're going to use the calculus for, times x plus 2. So we need a slope generator to get the slope. So I'm going to find the derivative implicitly of the given relationship. The derivative of 9x is, in terms of x, is 9 minus 4y dy dx plus 24 dy dx, and the derivative of 36 is 0. I'm going to factor the dy dx out of my those dy dx terms, which will leave me with negative 4y plus 24. I'm going to subtract the 9 to the right-hand side, and therefore dy dx is equal to negative 9 divided by negative 4y plus 24. I have a slope generator, and this slope generator is y dependent. So to find the slope at -2, 3, I'm going to substitute the y value. So at negative, I believe that was my point, yes, -2, 3 is negative 9 divided by negative 4 times 3 plus 24, which is negative 9 over 12, which is negative 3 over 4. That's the slope of the tangent line. But we weren't looking for the slope of the tangent line. We wanted the slope of the normal line. Perpendicular lines have opposite reciprocal slopes. Therefore, the slope of my line is not -3/4, but the slope of my line is 4/3. So I know there's a lot of algebra involved here, and you're going to have to take it slow and easy. And if you need to replay the video or parts of it, you can do that.